Section 1.1, we're going to keep looking at problem solving in this section. We're going to take another look at an example that is similar to Gauss's problem. So this was the example that we ended on last time, where we had numbers, but they still increased, every single time by 1. And I wanted to show you what would happen if the numbers didn't maybe increase by 1. Like, we could use even a very similar example. In fact, I'll use an example similar. Well, I'll make one up. We'll just make one up because that sounds like fun today. This doesn't always go well, so I'm going to apologize in advance if me making something up does not go well today. So we're going to make up an example, and I'm going to make it not start at 1 and also not skip by ones. So how about we start at 12, and we will do evens. 12, 14, 16, and we'll go up to, somebody give me an even number.
30.
Higher.
50.
100 and what'd somebody say? 120. That's good, because we wouldn't really want to add all those together, right? See, like if it just said 30, you guys wouldn't do what I'm telling you to do. You'd just add them together and grab a calculator, right? Yeah, you would. Okay, so here's our set of numbers. It's got two features of it that make it a little trickier to compute. Number 1, it doesn't start at 1. And number 2, it doesn't have every single number in the list. Now, the process starts out very similarly, right? What we would have tried to do was what we had done with the others, where we write all the numbers out. And then, do you remember what our next step was? Yeah, to write them backwards. So we would have had 120 here, and then it'd be 118, and then it'd be 116, all the way down to 12. Okay, so this gives me double the sum I started with. That's where that 2 comes from. And what are each of the sums going to be? 132. You're right the first time. Yeah, 132. So there's a bunch of 132s, correct? So far we've done nothing different. In terms of our actual process. The part that makes it tricky is we have to figure out how many of these there are. And they didn't start at 1, and we're skipping numbers, correct? Okay, so let's deal with the fact that we're skipping numbers first. Okay, let's pretend it started at 1 and had all the numbers in the list. Okay, so how many numbers would be in this list if we had all of the numbers, we weren't skipping anything, we started at 1, how many numbers would we have? 120. But we only have the even ones, so we're really only going to have 60. Okay, so how did we get from 120 to 60? We divide by 2. Why did we divide by 2? Because we only have the evens, so we only have half the numbers, right? What if it skipped every third number? Like what if we had, only every third number, I should say it that way. We would divide by 3. If it was every 5 numbers, we'd divide by 5, okay? So however you're skipping is what you're ending up dividing by, because you eliminated quite a few other numbers. Okay, but we don't really have 60 because we didn't start at 1, correct? We actually started at 12. All right, so there's a couple of ways to do this. I'll show you the way that maybe is my default on how I think about it. What number is right before the 12? 10. Okay, there's 10 there. I'll explain why this works. But this is the way I think about it. We have 120 numbers, okay? And we are going to subtract the number that's in the pattern that comes right before. It would have been 10. All right? So what would 120 minus 10 be? 110, yeah. And then we will divide by 2 because we're skipping every other number. So what would 110 divided by 2 be? 55. So there are 55 numbers. Let me explain what we're doing in terms of what we've done before. 55 times, I'll write times. There are 55 of these in this list. All right, so think about what happened. We are missing all the even numbers that come before 12, correct? So let's list them. What are they? 2, 4, 6, 8, and 10. How many numbers are we missing? 5. So when we did this, we ended up at the end here subtracting off 10 divided by 2, which is 5. Okay? And it's actually what we did over here. We just didn't have to do the division. When we looked at how we got these numbers, we looked at how many numbers were in front. Right? What was the number right before this in the list? Well, it was 35, right? And it was exactly 35 because we were using every single number. But over here, we're skipping numbers. So I looked for the pattern number that's before it in the list. The one that was in this pattern that would have come before it would have been 10. Whatever the pattern is, it's that one that we subtract instead. Just like over here, it was the number that came before it in this pattern, and the pattern here was subtracting 1 every time. Okay? If you don't like that pattern or don't like that process, you can count them like we just did, right? We said that if we'd gone from 1 to 120, there'd have been 120 numbers. We divided by 2 because we only had the evens, correct? There were 60. And we could actually count up the ones that were missing. Well, we were missing 2, 4, 6, 8, and 10. We were missing 5 numbers. What's 60 minus 5? 55. So it's still the same 55 numbers. Okay, let's finish this out so that we can say we've completed it. There's 2s now equals what? 132 times 55. Somebody grab a calculator for us. What is 132 times 55? I remember I made the numbers up, so I don't have the number, does it all? Oh, Caitlin's got one for us.
7,260.
Thank you so much. And then what would we do?
Divide by 2.
Divide by 2 because it's removing that double counting, right? All right, so what's 7260 divided by 2? It is. Yeah, 3,630. Okay. You'll have more opportunity to practice more of these in your homework and your group work. All right, let's move away from this particular strategy and look at something different. All right. If a soccer league has 10 teams and each team plays every other team once, how many games will the league manager need to schedule at the start of the season? So first, our list of what we do, we understand the problem. Do you understand the perspective of what's going on? You're playing on a soccer team, or maybe your kid is, or your niece or your nephew, and there are 10 teams, right? So how many teams will your niece or nephew or you, how many games will you play? 9. You'll play 9 games, right? Okay. But every team with which there are 10 playing 9 games doesn't sound quite right. There are not 90 games. Okay? So we are going to do this by examining a simpler case. We're going to break it down into a smaller number of teams and see if we can figure out what's going on, and then we'll be able to generalize that to a bigger number of teams, namely our 10 teams for what's going on. So what I'm going to suggest is that we do a 3-team scenario. So we're going to examine what would happen if we had 3 teams. And just so that it's easy to sort of manipulate with, our teams have super cool names, A, B, and C. Super cool, right? You're on Team A, Team B, or Team C. Okay, so Team A plays Team B, and Team A plays Team C. So these are sort of the games that I'm listing out. Team B plays Team A, and Team B plays Team C. And Team C plays Team A, and Team C plays Team B. So it sort of kind of looks like there are how many games? 6. Are there? No. Why are there not 6 games? Some of them are repeating, right? In fact, how many of them? Can you tell, Sally? They're all repeated in there, so there's only 3 games. Okay, so like if this is A and B, then this is a repeat, right? And this is AC, then CA is a repeat. And if this is BC, then CB is a repeat. So there's half as many games as we originally wrote down. Agreed? We started with 6, I marked out 3. Well, where did the 6 come from? Why did we have 6 to begin with? There were 3 teams, right? How did we get 6 games? So each of the teams, how many teams? We have 3 teams. How many games did each team play? 2. They each played 2 games. This is where our 6 came from. We had 3 teams, and each team played 2 games. 3 times 2 is 6. But we realized that when we did that, what did we do? We what? We repeated. In fact, we repeated everything. That's what Sally mentioned, right? Everything was repeated. We double counted, didn't we? Everything was counted twice. So in the end, what we had to do then is we had to divide by 2 because this removed the double counts. Okay, so let's think about generalizing that now to our 10 teams. Now, I made mention earlier, if you are on one of those teams, how many games are you going to play? 9, right? You're going to play every other team. So there's 10 teams. They each play 9 games. And then what are we going to have to do? What did I do over here? I need to remove the double counts. How did I remove the double counts? Divide by 2, because everything was double counted, right? So we can do the exact same thing here. We have 10 teams, and they each play 9 games. But if I were to list them all out, the exact same thing would happen again. I'd list every game twice. Because if team, Dolphins plays team Penguins, then playing team Penguins is going to play team Dolphins, right? It's going to get listed twice every single time. So I will have to divide by 2 to remove the double counts. So what is 10 times 9? 90. And 90 divided by 2? 45. So it's 45 total games. That matters, right? Because you're going to have to schedule them, you're going to have referees for them, and all of that. You need to know how many games you're going to actually have played on your fields in order to make that work. So this is an example of taking something where you may not have known exactly how you were going to do it at the beginning, but by making the numbers smaller and coming up with a strategy to do that, then you can expand it to a bigger scenario. Okay, this is a fun example because it's probably not the strategy that you would do in your life right now if I asked you to do this problem. So let's take a look. A store sells bicycles and tricycles. There are a total of 15 cycles in the store, and there are 35 wheels on those cycles. How many of each type of cycle are in the store? So where have you most recently seen a question like this? ACT. And how would they probably have expected you to solve a problem like that on the ACT? Any idea, Sally? Some kind of a formula, probably an equation, right? X plus y equals something, and something times x plus something times y equals something else, and we get an equation, and we do a systems of equation, which starts to feel a lot like Algebra 2 from high school. Yeah? Okay? And that's fine. There's nothing wrong with that approach. I want to show you how to do a problem like this where it's accessible for younger kids, because I don't really think the equations is going to be accessible to the 3rd grader. And what we're going to do real quick is accessible to a 3rd grader. So that's pretty cool. Agreed? Yeah, it's pretty cool. So we're going to make a diagram. So how many cycles does it say that we have? 15. And the 15 cycles have at least how many wheels per cycle? 2. It's at least a bicycle, right? It's got at least 2 wheels. It might have 3 wheels. Okay? So you're going to draw, probably a lot better than I do, 15 bicycles. I'm going to show you what my bicycle looks like. That's my bicycle right there. Kind of looks like cherries. That's my bicycle. I've got one thing with 2 wheels, okay? So I'm going to create 15 of these guys. I know I cheated because I used copy paste. Sorry about that. I mean, I wouldn't want you to think you actually have to be an artist to do the problem, right? That would be just such a disservice to all of you like me who can't draw. Okay, I have 15 cycles. Each cycle has 2 wheels, right? And they're all bicycles. So how many wheels do I currently have in my picture? 30. How many am I supposed to have? 35. So what would I do next?
Just
Add a few wheels. How many wheels do I need to add? 5. So I'm going to add 5 wheels, but they're tricycles, so I have to add them 1 to each cycle, right? I don't have a choice. It's not like I can add 3 wheels somewhere. I don't even know. Is that a pentacycle? Is that a thing? Probably not. Okay, so we're going to add 3 wheels. That's how exciting my wheel adding looks, just like that. You know what? It does the trick. We can count it. Do I have 35 wheels now? Yeah. How many bicycles do I have? 10. How many tricycles do I have? 5. And didn't you all think that was pretty cool now? I mean, really, seriously? That's a pretty good way to do the problem. I've seen this done before with chickens and cows and feet on a farm. Right? There's so many feet on the farm. There's so many animals on the farm. There's only chickens and cows. How many chickens, how many cows are there? You do the same thing, right? You draw chickens because they all have 2 feet. And then you'd add 2 feet per animal to get you your cow. Same idea. All right, let me write down my answer because I didn't do that. Oh, that wasn't right. Okay, so our answer, we need to make sure as we're answering word problems that we have units or words after it that describe what we're finding. This is 10 bikes or bicycles and 5 trikes or tricycles. So make sure we're answering the question that was asked. And you can check to make sure this works, right? Just looking at the actual things. So if you had 10 bikes, that's 10 times 2 is 20 wheels. And if you have 5 trikes, 5 times 3 is 15. And then 15 plus your 20 would be your 35 wheels. So you can check it to make sure that it's a reasonable solution at the end as well. All right, here's another fun one. We're going to use guess and check with this one. But we would be remiss if we actually didn't draw a little bit of a diagram just because it has a visual picture with this one. And we're going to keep track of our guessing and checking in a table. So in some sense, we're kind of using multiple strategies, but the basic overall strategy is going to be just guess and check. We have 48 feet of fencing, and we wish to make an enclosure along one side of an existing barn. What lengths would the sides need to be to have the greatest area enclosed for our chickens? So, we have a barn. I'm going to draw the barn. It's going to be really exciting. Are you ready? There's my barn. It's a cool barn, isn't it? And we are going to draw an enclosure along the side of our barn. So, anytime you're building along the side of an object, you don't fence along that side. I think you guys know that from a realistic perspective. I mean, like, you don't see fences alongside wooden, alongside the brick house, right? You don't see the fence lining along. You use the fence that's already there naturally, the house, okay? But every time people get to math, they want to put extra lines places, so just clarifying. So we have our existing fencing then, not existing, but what we're creating that we're going to draw. Okay, we know a little bit more than that. We know that we have 48 feet of it. And we want to make sure that we actually are able to calculate the area of our object. So in theory, we could make the enclosure whatever shape we want, but you do have to think realistically. Circle enclosure, not going to be real practical because then you can't use the side of the barn, right? Triangle enclosure, like if I tried to draw a triangle here like that, that's not going to give me the most bang for my buck in terms of area. So a rectangular enclosure is going to be the most reasonable enclosure to make. Now, you know some things about rectangles. Tell me something you know about a rectangle.
Yeah, so 4 corners you can.
4 corners. Yep, that's good. So we've got right angles at 4 corners. What else do we have? There's 4 sides, you bet. What else do we know more specifically about the sides that's useful? Yep. So like these 2 sides here are going to be equal, and these 2 sides here are going to be equal. But do we have to have all 4 sides equal? No, we could. It wouldn't hurt anything, but we wouldn't have to. Okay? So as we're thinking about our enclosure, we're going to have 2 of our sides, namely this one and this one, that are going to be equal. Maybe let's do it like that. And then the third side might be different, correct? Okay. So we've got our, we will call this width, and we will call this the length of our enclosure. And we are going to guess values. Now, we don't get to guess just anything we want, because we want to use all of the fencing. And how much fencing do we have? 48 feet. So I'll start us out with a rather random guess and say that, let's say that we had 10 feet for our widths. What would be the length? Where was my number? 48 total. 28. Yeah. Remember, we don't need this piece right here. There's not going to be a fence there. We just have the length here. Okay. So this is they have to add up to 48, right? 10 plus 10 plus 28, we got the 48. So this is our guess, and our question is, what area do we get if we guess that? So we haven't talked about area, but do you remember how to find area of a rectangle? Yeah, so area equals length times width. So my length is 10, or my width is 10. My length is 28. What's the area inside my rectangle? 280 feet squared. Good. So we have feet squared or square feet, 280. Now this is just our first guess. We have absolutely no way of knowing after one guess if we're right or not. Agreed? We're going to have to make several guesses before we can have any idea if we've given even a good guess to start with. So I need another guess. Somebody give me another guess. Start with the width. 12. Okay. So if I do a 12 for the first side width, then the other one is also 12. What would the length then be? 24. And if we multiply the length times the width, what do we get for our area with 12s? So our 12 times 24, that's our goal right now. 288. And you even got the feet squared in there. Fantastic. So was our first guess correct? No, because I found something that's bigger. But right now, I don't know if it's the biggest. I just know it was bigger than the first guess. So we need some more guesses still, right? All right, I need another guess. 15. So I do 15 and 15. That's 30. What's left? 18. All right. What would the area be if I had 15, 15, and 18? Okay. So for a little while there, I went from 10 to 12. Increasing the width looked like it was increasing the area. But at some point, because when I went from 12 to 15, that didn't happen anymore, right? It went back down. I've got less than I had before. So it would not be reasonable right now to go up to 16. Are you guys with me on that? The answer's got to be somewhere between 10 and 15. It might be 12, it might not, but it certainly is not bigger than 15 because we're starting to go back downhill in terms of our number of our square footage and area. All right, 288 still looks pretty good. That's my best guess. How can I see whether or not it is the best guess? I need some more numbers. What do you want to try? 11. Okay, 11 would be a good shot. Let's try 11. So if I do 11 and 11, it's 20 what?
26.
That's 22, and then I have 26 left, right? What would the area be inside of my enclosure? You're close. 286. So which one's my best guess so far?
12.
Still the 12, right? And I think somebody says we also wanted to try what? What did you want to try? 13? Let's give 13 a try. Because it's just on the other side of 12. 13, 13, and what? 22? And what would the area be?
286 feet squared.
Ooh, it's also 286 feet squared. So slightly smaller. So these two are on the either side of our 12, 12, 24, and they are slightly smaller. What's our best bet here for our enclosure? The 12s, right. So it says what lengths, we need to make sure we're answering the question, right? Does it ask for area? Does it ask for lengths? What does it actually ask for, right? It says what lengths would the sides need to be to have the greatest area enclosed for our chickens? One of them would be 24, and the other two would be 12, right? So 12 feet, 12 feet, and 24 feet. So generally speaking, you need several guesses before you can decide that your guesses were actually good ones, right? You're going to have to guess and check several places. Okay, one more example. This is a case of working backward. The problem goes something like this. One winter night, the temperature fell by 15 degrees between midnight and 5 a.m. By 9 a.m., the temperature's numerical value had doubled from what it was at 5 a.m. By noon, it had risen another 10 degrees to 32 degrees. What is the temperature at midnight? Okay. So what do you think you might do to start a problem like this?
32 raised.
Okay, so you're going to have to start at the end of the problem, right? And then work our way backward. There's a lot of time frames that they're giving me. Would it be okay with you guys if we wrote down all the time frames so that we can figure out where we are in the process of working backwards? Okay. What's the time frame, the earliest time frame that it talks about? Midnight. And the next one was 5 a.m. And then 9 a.m. And then noon. Okay, so these are our time frames that we're given. And they give me some temperatures and how they change. Let's just go from the start to the end on how they change. What happens from midnight to 5 a.m.?
It drops 15.
It drops 15. What about from 5 to 9? It doubles. At least its numerical value doubles. Doubling temperature is a weird thing because do you double the Celsius or do you double the Fahrenheit? Yeah, so we're not talking like, we're just looking at the number, just the single number talking about. What happens between 9 and noon?
Rises, added 10.
Yeah, it adds or rises 10 degrees. Okay, so this is sort of how it's changing. And then they give us one numerical value that we know. What is it and when? 32 degrees at noon. So at noon, it's 32 degrees. So that corresponds to noon. How can I figure out what happens or what it is at 9 a.m.? Subtract. I need to work backwards. It said it rose 10 degrees and it arrived at 32. So where did it rise from? 22, right? So at 9 a.m., it was 22 degrees. It went from 22 to 32 and it rose 10 degrees. What about 5 a.m.? It had doubled. So you'd need to divide. You're going to go backwards and you divide by 2. So that would give you 11 degrees. And then at midnight, what would I have to do? Yeah, whatever the value was, it would have had to have been subtracted by 15 in order to give me 11. So going backwards means I would add 15. So if I add 15 going backwards, what will that give me at midnight? 26. 26 degrees. Now again, our answer needs to be written as our answer. It was 26 degrees at midnight. Okay, one more little bit before we go into our groups. I want you to take a look at the 12 days of Christmas. There's an example problem, and I want to make sure that you remember which gifts are given on which day, so that when you get to the problem, you're not like, I don't know, it's not Christmas. I'm not saying that anytime soon, right? Okay, so on the 12 days of Christmas, the first one's a partridge in a pear tree, so that's fine. And all the other ones are written down. But these are the religious symbolisms for the 12 days of Christmas, which I think is pretty cool. And so maybe you've seen these before, maybe you haven't. So our first one is true love represents God. The 2 turtle doves represent the Old and the New Testament. On the third day, it was 3 French hen. Those represent the virtues, faith, hope, and love. Number 4 is the 4 calling birds, represent the 4 Gospels. The 5 golden rings are the Pentateuch, which is the first 5 books of the Old Testament. 6 geese a-laying stand for the 6 days of creation. 7 swans a-swimming are the 7 gifts of the Holy Spirit. 8 maids a-milking are the 8 Beatitudes. 9 ladies dancing are the 9 fruits of the Holy Spirit. The 10 lords a-leaping are the 10 commandments. The 11 pipers piping are the 11 faithful apostles. And then the 12 drummers drumming are the 12 points of doctrine in the Apostles' Creed. So as you work through these, which you will have on one of your examples in your group work, reference this if you need to figure out how many of what you had on which day kind of question, okay?